Good evening, everyone. Thank you for being here today. Today, we're going to talk about a topic that speaks close to my heart, which is fractions. So most of us know that fractions are hard, and a lot of children, adolescents, and adults struggle to learn fractions. So today, we're going to talk a little bit about interventions. This symposium has been organized by Alex, who is a PhD student here at UW-Madison. And the first speaker today is Jing. Jing, are you ready to start? Okay, so we're gonna do the traditional format. So a talk, and then we open for questions, and then we can also have some discussion at the end. Thank you. You may start whenever you're ready.
Okay, thank you, Bella, for the introduction. I'm going to share my screen right now. Okay. Alrighty. Hello, everyone. My name is Jing Tian. I'm a postdoc working with Dr. Gunderson at Temple University. Today, I'm very excited to share with you results of our recent intervention on improper fractions with the number lines and area models. I don't need to convince any of you here that learning fractions is very important for success in school and beyond. However, it remains a challenge for many children to develop mastery of fractions. Therefore, it has been a goal for researchers and educators to develop more effective fraction instruction. So in this talk, I'm going to focus on one particular aspect of fraction instruction, which is visual representations. So US math textbooks typically present fractions with the area models in grades 1 and 2. And here I'm showing you an example of an area model representing the fraction of 1/4. And later fractions representing fractions with number lines were introduced. And here is an example of the number line showing the fraction 1/4. So there have been several interventions focusing on building children's fraction knowledge with the number lines that yielded better learning outcomes than regular school curricula, suggesting that the number lines are very effective in teaching fractions. So Hampton and Gunderson 2017 directly compared the effect of using number lines and area models in teaching fractions. In this study, they randomly assigned second and third graders to a number line training, an area model training, or a non-numerical control condition. After a brief training, children who received the number line training or the area model training became more accurate at estimating fractions on the trained representation than the children from the other two conditions. Critically, children who received the number line training were also more accurate at magnitude comparison, which none of the children were taught about. So these findings really suggested that the number lines as compared to the area models are more effective in teaching children fractions. These findings were later replicated by Gunderson 2019. So in the current study, we were hoping to extend these prior findings on the advantage of the number line over area model to teaching improper fractions. So to represent improper fractions, if you want to do that on a number line, you only need to extend the line beyond 1. It still remains to be in the same model. However, if you want to do so on an area model, you need to draw a separate identical area model just as the first whole. So we think there are reasons to believe that the number line will also be more effective in teaching improper fractions. In this current study, we administered 3 sessions. In session 1, children completed a pre-test on fraction knowledge, which I will describe in more details later. In session 2, we administered the intervention, which was closely modeled on the procedures in the 2 prior studies that showed the effects of children's learning on proper fractions. We randomly assigned children to a number line training and area model training, or they were asked to complete some crossword puzzles as a control activity. Immediate post-test was administered right after training in the same session. Children also completed a delayed post-test 2 weeks later. We were trying to see whether if there are any training effects, whether this will remain after 2 weeks. So we registered the study on Open Science Framework, and then we recruited, run 133 4th and 5th graders for the study. 119 of them were included in the analysis because some children did not complete all the tasks within the pre-designed time frame. We had 4 tasks for our pre and post tests, including the number line estimation and area model estimation, similar to what children were trained on for the number line training and area model training. So in these estimation tasks, in the number line, children were asked to estimate fractions on 0 to 3 number lines. Area model estimation involved 3 blank squares. Children were also asked to complete magnitude comparison and comparison to 1 task, which we viewed as transfer task. So they were asked to compare the sizes of fractions. As I mentioned before, the training was closely modeled on prior studies. In the number line training, children were introduced to fractions as numbers that had a number on the top and a number on the bottom. They were also told that the number lines that they use in the training goes from 0 to 3. To represent this fraction on the number line, they had to segment the number, each unit of the number line based on the number on the bottom, which is 2 in this case. And then they have to shade the segments based on the number on the top, which is 3 in this case. And finally, they only need to place the fraction at the end of the shaded segments, and this represent the fraction 3 over 2 on this 0 to 3 number line. Children were showed a couple of examples like this with different fractions, and they then practiced doing this on their own, receiving feedback from the experimenter. The area model training was the same procedure as the number line training, except for that area model instead of the number line was used. So first, I want to share with you the results of our pre-registered hypothesis. So we first explored whether children who learned with the number line or the area model improved after the training on estimating fractions on the model that they were trained on. We used percent absolute error to indicate children's accuracy. So a lower PAE is associated with more accurate estimates. Unexpectedly, children who received the number line training as represented by the orange bar here did not do any better than children from the other 2 conditions on estimating fractions on the number line. So the number line training was not effective in this case. In contrast, we did see that children who received the area model training, which is represented by the yellow bar here, were more accurate at estimating fractions on the area models than children from the other 2 conditions. We then explored whether the training effects were the same for both the trained and untrained fractions. So some of the fractions in the pre and post tests were involved in the training and some were not. As what we were hoping for, children who received the area model training did improve on both the trained and untrained fractions on area models. And critically, we originally predicted that children who received the number line training will also have better fraction magnitude comparison accuracy than children from the other 2 conditions, which does not seem to be the case, given that we did not see any improvement after the number line training, given the results of our hypothesis 1. But at this point, we were hoping to see that the area model training had some transfer effect to this magnitude comparison. However, children from the 3 conditions did not seem to differ at all on this task. We then ran a couple of exploratory analyses. The first set I'm showing you here was trying to look at the scope of improvement after the area model training. We found that the training led to more accurate estimates of both proper and improper fractions on the area model. We also found that the improvement in the area model estimation did not transfer to the other comparison task, which is comparison to 1. And then lastly, we find that the improvements in the area model estimation after the training did remain on the delay task 2 weeks later after the training. The next set of exploratory analysis was trying to understand the lack of improvement after the number line training. We found that the number line training did not even lead to improvement in estimating the trained fractions on the number line. We also did not find improvement in estimating proper fractions, which the 2 prior studies did show improvements. Finally, we looked at the number of errors children made during training, and we found that children who were receiving the number line training made more errors than those who were receiving the area model training, suggesting that the number line training was more confusing for children than the area model training. So to sum up, unexpectedly, we did not see any effects for the number line training in this current study. One possible reason is that the training was hard to follow, as suggested by the more errors they made during the training. Another possible reason was that the models we used in the training was more different than the pre and post tests. So here, I'm showing you the number line models that we use in pre-post test, which was a pure line going from 0 to 3. And what we used in the training was a 0 to 3 thin, long rectangle. Although these were the same as in prior studies, we thought this might be a reason that we did not see any effects right now. And we did see that area model training led to improvements in estimating both the improper and proper fractions. However, this improvement did not transfer to other tasks. Some possible reasons for these intervention, we think it might be that the improper fractions just require more training and they are harder to learn than the proper fractions. So a 15-minute training may not be enough, and they may become confusing to be combined together with proper fractions. Another possible reason is that the 4th and 5th graders who participated in the current training, their learning of fractions may actually be harder to improve than the 2nd and 3rd graders because they've already learned some fractions from formal math classes. So these are possible things that can be explored in future studies. Finally, I'd like to thank our funding sources, the children and teachers who participated in the current study, and members of our lab who helped with the study procedures and data entry. Okay, and thank you everyone for listening.
Thank you for the amazing talk, Jing. Alex is the next, and I think that maybe as she's setting up, we may have time for at least one question. Thank you.
Yeah, I have a question actually. Thank you. That was a great talk. I guess I wonder if you could elaborate a little on what might have made the number line training hard to follow.
Okay. I'm not muted, right? So we think one reason for the number line training harder to follow is because number lines might be more challenging than the area models for children in general. There have been some studies showing that children were generally more familiar with area models than the number lines to represent fractions, possibly because area models were actually used more often in math class. So maybe they came to the study with less knowledge about representing fractions on the number line as compared to the area model. Yeah.
Thanks.
We also had a question from Martha in the chat. Martha, I don't know if you would like to speak out aloud or if we can just read your question, but feel free to join and speak up in case you want.
Hi, I just want to say that a little bit has already been answered in the answer to David's question, but I was curious about the nature of kids' prior experience with the area model versus number lines or tape diagrams, which is what some people call the thin rectangular strip that you used in the intervention.
Yeah, thanks for the question. I actually can't see the chat right now as I'm sharing my screen. But one caveat of this explanation that I just shared is that we do not see difference on the pretest for the children's estimation on area model and number lines. So even if they are more familiar with the area model, they were not more accurate at estimating at least both improper and proper fractions on the area model than the number line in the pretest. So maybe there are some implicit knowledge of area model that we did not capture in the pretest, but there are definitely more open questions to be answered relevant to this question. Yeah.
Thank you. Because of the time, I think maybe Alex, you should start, and then maybe we can discuss that more at the end. Thank you.
Thank you, everyone.
Sounds great. Thank you so much, Jing. And I'm going to try to, can you see my slides okay?
Yes.
Awesome. Okay, great. So my name is Alex Viegut. I'm really grateful for all the speakers and to all of you for being here. I'm excited to continue talking about fractions. This is something I love a lot. So I'm going to present work titled From Number Sense to Fraction Sense, Using Analogy to Improve Fraction Understanding. And this is work that I've done with my advisor, Percival Matthews at the University of Wisconsin. So as we've already heard, fractions are difficult for many students, and fractions are also, as we all know, very important. So kids' fraction sense, or their ability to judge the sizes of fractions, is very important for things like algebra, and then in turn, algebra is very important for higher math. So we know fractions are important, but we know a lot of kids struggle with them. So there's lots of ways to think about how we might help kids with fraction learning. The way that I approached this project was to think about, what do fraction learners already know? What do they bring to fraction learning that might help them and improve their fraction sense? So one of the things that fraction learners already know is they already know a lot about whole numbers. They know how to estimate whole numbers on number lines. For example, a kid in first or second grade would have a really easy time typically judging a number like 3 on a number line from 0 to 10. And this shows that kids really can estimate relative magnitudes long before they learn fractions formally in school. So to judge the position of 3 on this number line, and I'm realizing that you can't see my cursor probably very well, but to judge the position of 3 on this number line, children have to judge 3/10 of the line, right? They have to figure out what proportion is 3 of 10. And the relation between 3 and 10 is the same as the relation between 3/10 and 1. So a child who can judge 3 out of 10 on this number line does have some sense of how big 3 out of 10 as a fraction is. But this connection does seem kind of obvious when I present it like this, and it might seem obvious to us as adults who are familiar with these ideas, but children definitely don't always recognize or use this analogy. So we were thinking about how we might help kids see that their whole number knowledge is relevant to the fraction estimation in this way. So we asked, can alignment help children notice and use this analogy? So I aligned the whole number and fraction on the previous slide. Can alignment help children? So Gentner and other analogy researchers have shown that alignment of a familiar base domain and an unfamiliar target domain can make structural similarities between the base and the target more salient. For example, Thompson and Opfer showed that using the base of small powers of 10 whole number estimation, so like 0 to 100, was helpful for showing kids how to estimate whole numbers on larger powers of 10, like 0 to 10,000. So we wanted to use this same idea to help kids see the similarities between the whole number base and fraction estimation as the target. So the research question then is, does practice with aligned whole number and fraction number lines help children use this analogy to improve their fraction knowledge? So to test that, we had 43 children in 1st through 3rd grade, and we randomly assigned them to 2 conditions. So half of the children were assigned to an alignment intervention condition, in which we taught them this strategy for putting fractions on number lines. To figure out how big 3/4 is, for example, we taught them that they could draw an extra number line to help them. They could draw a number line from 0 to the denominator, in this case 4, and figure out where the numerator, in this case 3, goes on that line. And then if they know how big 3 is relative to 4, then they know how big 3/4 is relative to 1. So we taught children this strategy in a scaffolded sort of situation with about, the intervention was about 10 minutes. And then half of the children were assigned to a non-alignment control in which they saw exactly the same problems, exactly the same whole number and fraction estimation problems, but they weren't lined up. And there wasn't the same sort of alignment or color coding or gesture that was meant as a cognitive support in the alignment intervention condition. The non-alignment control, they could have used the analogy, right? Because they were doing the same problems, but they weren't lined up, so it was harder for them to make that leap. There also were some addition and subtraction problems in the control condition to control for time on task. So this intervention took place at session 2 of a 2-session study. So at session 1, we gave the pretest in which we tested kids' whole number estimation skill to make sure that their whole number estimation skill was better than their fraction skill. And then we also tested fraction estimation and fraction comparison at pretest. Then at session 2, we gave them this about 10-minute lesson. And then immediately following that gave a post-test, which was identical to the fraction pretest. So there were estimation tasks or estimation trials, which we see as a learning task. We taught them how to put fractions on number lines. Did they improve at putting fractions on number lines? And then a comparison task, which tests the transfer of this new skill. So are they able to use this analogy still? Is it still helpful to them when the number line context is removed? So first, let's look at the learning results. So did the intervention group learn the target task of fraction estimation? Here I'm plotting PAE or error, so lower is better. And so at pretest, both groups had pretty high error, which is not surprising. These were young kids who didn't really have a lot of experience with fractions before. And then at post-test, the control was unchanged, but the intervention group had much lower error than the control. And this reduction was about 40% reduction in their errors, or their percent absolute error. And this effect was significant when we control for pretest, age, and whole number skill. So this is great. It suggests that kids did learn the target task, but like Jing, we also wanted to know if this held for trained and untrained items. So I'm calling this near transfer. Did it help not only with fractions that they saw in the task, but also with new fractions? So here we're gonna look at the top left quadrant first. I'm plotting the given fraction, or what they should have estimated, on the x-axis, and the median estimate, children's median estimate, or what they did estimate.
Did you bring me your phone?
Oh, sorry. If you are not speaking, if you could just mute your mic, that'd be great. Thank you. Okay, so yes, so let's look here at the pretest for the trained items. Both groups are equally inaccurate. And then at post-test, the intervention group is much closer to this perfect dotted line, right? So this is great. When we look at the untrained items, we see a very similar pattern that this intervention did transfer, did help children even with novel fractions, which suggests that kids were able to use this analogy even after we removed those alignment supports. So there wasn't an extra number line written for them at the post-test, right? So they had to imagine or draw that on their own and use this analogy in a new context. But we also wanted to test, does it really transfer when we remove the number line altogether? Does it help them compare fractions? So here I'm plotting accuracy, so higher is better. And at pretest, children were about at chance, a little bit higher than chance. And at post-test, neither group changed. So the intervention did not transfer to fraction comparison. And one of the reasons for this, we think, might be that the intervention did not scaffold comparison directly. So children may not have realized that this new strategy for placing fractions on number lines was relevant or useful in a comparison context. So to sum up, the intervention, this 10-minute intervention did lead to big improvements in fraction estimation, even for untrained fractions, but it didn't help them compare fractions more accurately. So I think overall, this does suggest that kids can use their knowledge of relative magnitudes of whole numbers to help them with fraction estimation, but only if we give them support for the analogy. The control condition without support, without the alignment, was not helpful. So for future directions for this work, as I mentioned, I want to scaffold comparison directly and show kids that they can compare fractions by placing both fractions on a number line and then comparing them. I also want to compare it to something like what Jing was talking about, to a more traditional partitioning intervention. A more active control, I think, would be really interesting to see what each of these different interventions helps children with or doesn't. And I also have been thinking a lot about what fraction learning or fraction knowledge really means and what kinds of outcomes are relevant here. So I want to expand to include some outcomes that math education researchers have used, but that we as psychologists tend to not use in our work. So for example, what fraction is the smaller stick out of the longer stick? Or this rectangle represents 3/5 of a candy bar. Draw a picture of the whole candy bar. So I'm interested in how some of these lab-based interventions might influence or not influence kids' fraction reasoning on tasks like this. And lastly, I just want to give 3 questions that I think we should all be thinking about in this intervention, but also in all of the interventions that are presented today. So 1, what are the lasting effects? Jing used a delayed post-test, I did not, and I think a lot of lab studies don't. So I think that's a really important question. What population is this intervention effective for? So would this one have been effective for older students, or for how could we have modified it for kids who didn't start with good whole number estimation skills? What populations are our interventions effective for? And then lastly, delivery. So especially in this context, how well does this intervention work when delivered virtually? This intervention I did pre-COVID, so it was in person, but the follow-up we will be doing virtually. So I'm excited to see the results of that. So with that, I will just say thanks to all the participating kids and families, to my lab, and to all the research assistants and the funders. Thank you all very much.
Thank you for the great talk. And yeah, again, I think we have time for at least one question. And also Elizabeth sent some comments on the chat.
Alex?
Yeah.
Do you find age effects, like with, you said you had children from 1st grade through 3rd grade?
3rd grade, yes. So
how did the 1st graders fare on this?
The 1st graders improved just as much. There was no significant effect of age. We did find that in pilot testing that the 3rd graders that we were getting were already quite good at estimating fractions on 0 to 1 number lines. So we definitely don't have a representative sample here. These are the kids who are willing to come to the lab. Yeah.
Okay, thanks.
Thank you.
Okay, we had a question from Charles. Would you like to ask about a lot?
Thanks, Charles. Great question. So Charles asked, did you see children use the trained strategy at post-test? Did they draw the whole number line? So the answer to that is some kids did, some kids didn't. The majority of kids did not draw the extra number line. We didn't ask kids for their strategies in the post-test tasks, but we did have a separate task where we asked about strategy that we're still sort of working through. But we did see that some kids did, but most kids did not actually draw the number line. In the strategy reports, some kids talked about imagining the extra number line or just imagining the 1 as a different number. Yes, great question. I think strategy reports are really important here, and we'll keep looking at that with the follow-up.
Cool. Thanks, Alex.
Thank you. All right, I'll turn it over to Nancy.
Okay, thanks. I hope everyone can see the screen. The title of our talk is Building Fraction Sense in the Classroom. Wanted to acknowledge my collaborators, Nancy Dyson and Kelly Giselli, as well as IES, who has been supporting this research for the last 5 years. Okay, now. I don't know why oh wait, let me try this. Here we go. Okay, as you all know, math difficulties are widespread, and these statistics keep me up at night. These are statistics from the recent US report card based on the NAEP data, and you can see that overall just 34% of 8th graders nationwide are proficient, but the situation is especially dire for higher risk populations. And if you look down at the students with diagnosed disabilities, only 9% were proficient. So as has been mentioned in all of the great talks this morning, fractions are a crucial domain of math education. And we have found that and other research has also shown that students who leave 6th grade without fundamental understandings of fractions are likely to experience cascading difficulties that lead to lifelong avoidance of math. And at the same time, there is a great need for validated interventions in this age group, 6th grade, to circumvent this cycle of failure. So as people have talked about today, the importance of the number line and learning on the number line. And the reason it's important, especially for older students, is it broadens the concepts of fractions in ways that traditional part-whole representations can't. Young children, especially those with learning disabilities, because it's easier to teach, the instruction often over-relies on pi model interpretations of fractions that can lead to narrow thinking about what fractions represent. And so it's important to expose children to different types of models. Number line representations of fractions in particular help students see that there are fractions between whole numbers and that fractions can be less than, equal to, or greater than 1, because some of our earlier studies showed that even in 6th grade, a lot of students interpret fractions as being very, very small and less than 1. So to address this need, we developed a fraction sense intervention for 6th graders who are struggling. I mean, they're children who really have significant difficulties. The intervention's intended for supplemental use in response to intervention classes. The idea is to build foundational knowledge with number line and related representations to empower math learners to profit from instruction in general education. And then our final, most challenging goal is to make the intervention usable by all intervention teachers who, at least in the United States, often have variable training in math and special education. Some have very minimal in either one. So this is our theory of change that motivated all of our interventions, and I'm not going to go through this in detail, but basically the idea is that we want children to learn that fractions, to see fractions as numbers, to understand fractional equivalence and ordering, and then of course fraction arithmetic. Our foundation was based on the principles of the science of learning. So you could see those listed there, things like gesturing to promote learning, integrating visual and verbal models, and of course, lots of distributed and interleaved practice. We felt like we wanted to change in terms of the underlying cognitive processes, basically numerical magnitude understanding, among other things. Proximal student outcome would be improved fraction knowledge. And then of course, down the road, we hoped that by improving fraction knowledge, we would also improve overall math achievement, self-efficacy, increased algebra awareness, and of course, for children or for students to use fractions in their daily life. So this is the overview of, we had multiple iterations of development. First, we developed and tested the intervention with teachers. And I think I presented some of these data at a previous MCLS meeting. But then in year 3, we started to work with collaboratively with teachers to train them to carry out the intervention. And what I'm going to focus on more today is year 4, when we tested the effects of the intervention when carried out by 6th grade teachers. This is our basic design for all of our studies. And in terms of instructional strategies, these are the things that we focused on throughout the intervention. Because our children were very delayed, we wanted to develop deep understanding, so we focused mainly on familiar fractions so they could understand all of these important concepts related to equivalence, understanding the meaning of the numerator and denominator and how they work together, finding benchmarks on a number line, and always thinking about asking of what to find the whole. So this is a summary of the first 3 studies that we have done and published or presented. And you can see what the sample was similar across the studies. but we had somewhat different research designs and measures. But you can see in study 1 and 2, the intervention was carried out in small groups of 4 children, with the instructor being someone from our research team who was specifically trained to carry out the intervention. In the 3rd year, we found that groups of 4 wasn't very practical in terms of what is actually happening in schools. So we thought, oh, let's try carrying out the intervention in the more typical type intervention setting with larger groups of 12 to 15 students. And we put them on animated PowerPoint slides and presented the same way. And we still got quite good results. But the one thing that really stands out here is that we're getting decent effect size, except for the fraction arithmetic. Is still pretty low and insignificant in most cases. It may be, part of it is that kids in their regular intervention are getting a lot of help in this area, but also we did find that the children just are not making a lot of gains, which I'll address in a bit. Okay, so in terms of the implementation study, we mentored teachers, and they did actually teach the intervention independently. They taught every lesson. These children were very low. They scored below the 4th grade level in math, even though they were in 6th grade. So this is what we found. The effects were not as strong, which is not surprising, given that this was a school-based intervention and we had just trained the teachers. But you can see the effect sizes were not as strong, and also the fraction arithmetic, once again, even though we've been trying to improve in that area, are still minimal to none. So pluses and minuses, we did find that the teachers showed fidelity to the scripts and they were positive. We did find that because for fidelity, we had to keep the intervention pretty scripted. That kind of did limit questioning of students to really build understanding. We also had some problems in the schools in scheduling difficulties, so we weren't able to carry out all the lessons. And we had a pretty high incidence that year on students who moved in and out of the intervention and attrition, and lots of students with behavior IEPs that we had to deal with, but that's the real world. But the one thing that I wanted to just talk about briefly then is, and I know David's here, who's done a lot of work on fraction arithmetic. Fraction arithmetic is really hard to remediate with students with math difficulties. And they often come to middle school trusting procedures, but they misapply them in a lot of ways. And they have a lot of confusion thinking about addition and multiplication and those operations. And so basically our intervention developing conceptual understanding does not easily transfer to fraction arithmetic. And I just wanted to show you very quickly, these are some examples of errors that these entrenched persistent errors that we see. In green are the correct answers, and yellow means they're making some progress in their answers. And in the others are errors. And you can see that the children do tend to do things like, that they were okay with the easy ones with the common denominators, but then if they were mixed denominators, they tended to choose the larger one, and then they didn't adjust the numerator before adding, and so on. And then also similarly with multiplication, the common error is of keeping the denominator since it's the same in both fractions, and it's a typical addition multiplication confound. So that's, kids as they learn to add fractions and then they multiply and the procedure is different, they make mistakes. So we really want to focus on that. And one thing we're doing moving forward, because we have a new grant to expand this intervention, and we feel like it will be really, rather than teaching these separately, to really, for addition and multiplication in particular, to present the problems side by side. So all these, although these problems look similar, they have very different actions, models, and operations. and answers to the question. And we did these are like really simple problems with easy fractions, so children can understand conceptually without getting bogged down with all of the calculation with the harder numbers. But the idea is for them to talk about how to solve both these problems and then encourage them to make a model of each problem to avoid making mistakes. And so what we do with the modeling, and the other studies presented this morning have shown that, it's the number line model is kind of hard, and we found that too. So we also connect it to the area models with fraction bars that are on magnets, that children have a metal pan that they work with. And we're hoping that this will highlight some of those differences. And we do plan to provide, have much more attention to fraction arithmetic moving forward. And it's possible we just don't have enough time in our interventions, so we're going to kind of tone down the amount of concepts that we provide. So that's it. Thanks.
Thank you for the amazing talk. I would like to open that for questions. So feel free to type in the chat or to join us and ask. And the next one is Jake. So maybe if you want to start setting up while we have questions. Thank you.
So thank you, Nancy. If I have time for a question, I'll ask one. That was a great talk. I'm wondering about arithmetic. I guess I just have a trace of sort of old school in me, and I wonder if, I've read a lot of these textbooks, and I don't really see any of them doing the straightforward thing, which would seem to be, have a lesson where you say, like, look, you do this under these conditions, but not under these conditions. You keep the common denominator now, but you don't do it now. Here are the conditions under which you do each thing, and now let's just practice that. So, that seems depressingly old school, but I kind of have the sense that it isn't tried that much. And I wonder if we sort of have to give up and do that instead of putting as much emphasis on concepts. So that's my sort of provocative proposal. What do you think of that?
Well, I understand your point completely. But the only thing is that for children to even be operating on fractions without understanding fractions and fraction magnitudes is just like really, then the only way they can learn it is through kind of memorizing procedures that won't always work for them. But I do think you're right that we do need to provide a lot more structured instruction with the arithmetic along with the concepts. But our idea is if we can kind of present them together as opposed to like, okay, you start with addition and then you do, subtraction and multiplication, but if they can kind of see how and why these problems are different. But it is very challenging because there's so much goes into fraction arithmetic when you think about it. You have to know your multiplication tables, you have to understand multiplicative reasoning, it requires a lot of executive functioning and so on. And for children who struggle, that can create a lot of problems.
Can I add something to that? We found that students who have no understanding of what fractions are and what it means to add or multiply, you might be able to train them to do a page of problems, but that's pretty useless in the real world. We're hoping that when they have to do a recipe and they have to half a recipe or, add a certain amount of this and a certain amount of that it will make sense to them enough that they can come up with the right answer, even if they can't remember the procedure. Because students who struggle with math, you can say, oh, well, in this situation, you do this, and in this situation, you do that. They don't remember what the situations are. And then they just start moving numbers around and doing all sorts of bizarre, if you could see the number of procedures that students use, and they have been taught, because teachers do give up and just teach procedures, but they're so confused in between different operations. They cross multiply when they're supposed to be adding. They do all kinds of bizarre things because they're not really thinking about what the fractions mean. And so we're hoping to develop enough understanding that they can say, oh, well, it doesn't make sense to just hold on to this denominator when I'm taking a third of this fraction. That doesn't make sense, rather than just saying, what's the rule? What's the rule? Do I keep the denominator? Don't I keep the denominator? Does that make any sense?
Yeah, I guess I don't want to take up Jake's time, but we could discuss later maybe. I guess my question is partly motivated just by talking to some students who seem to do the problems very well and have mastered the procedures. I haven't yet found a single student who could explain to me why you multiply the denominators when you multiply fractions. So it seems like the students who succeed, it's not as a result, or at least it's not obviously as a result of their conceptual understanding. That's sort of behind the question.
Yeah, and that's, again, but our kids are so low performing, but we would love to talk to you more moving forward to be thinking about arithmetic, because I know your research is very, concentrated on that, and it's been very helpful for our thinking. Thank you.
Can I come in here? I would just like to say that I think the way that we label our work with fractions may be part of the problem. Working in a multilingual education system, and if I say multilingual, I say really many languages, one of which is English, that it's not so easy for kids to align. And I really loved the notion that came out earlier about alignment, that space and numerosity actually talk to each other. That's my bit today. Thank you.
Thank you. And I'm sorry, but I'm just thinking of time. I think maybe Jake should start and we maybe can continue this conversation after. And if people can stay longer, we can keep talking about it. Thank you, Jake.
Okay. Thank you all for being here. Thank you for organizing this, Bella and Alex. Yeah, so kind of continuing the discussion and then starting to think a little bit more about arithmetic with rational numbers. Today I'm going to talk about a classroom intervention that we carried out trying to develop students' adaptive rational number knowledge. And this is with 7th grade students, and this is with a suite of digital games, which we're calling game-based learning environment. And this is together with my colleagues from the University of Turku and Tampere University, and there are all the names. So the idea that we are basing our work on is this, going back to these ideas of there's being 2 types of expertise, routine expertise and adaptive expertise. And the contrast between the it's not necessarily the end goal of education or teaching about rational numbers. Yeah, so did my internet just cut out there for a little while?
It did, but you're back.
Sorry.
Yes, okay.
Yes.
Excellent. Right in time. Yeah, well, hopefully you read the slides and I'll have to move on. Yeah, basically comparing these 2, routine expertise, this more static knowledge. I think the point that I really would want to make there is this idea of what Nancy was talking about, being able to apply knowledge in contexts that haven't necessarily been explicitly trained. And so then the idea of adaptive expertise then being this malleable knowledge that's readily applicable in novel situations, including in future learning situations. As we saw, fractions are important for algebra, algebra is important for later math. This is a cumulative domain we work in. Right, so the example, one important thing is the idea that adaptive expertise and adaptive knowledge isn't necessarily just more routine knowledge, that this knowledge is actually qualitatively different. I'll actually have to skip over this example now since I kind of got short of time, but there's a really nice metaphor about adaptive versus routine expertise, and it involves navigating through streets, and routine expertise is knowing the ways that are very specific, but adaptive expertise is being able to find new ways based on this existing knowledge. And they're also being able to apply it in situations that aren't necessarily exactly like you trained. Yeah, but this has been used in math education research and math cognition research previously, this idea of adaptive expertise. And Dowker used it in the 90s with math experts doing mental calculations, and then using these friendly numbers, being able to flexibly work between numbers, and also the work with procedural flexibility, especially in arithmetic, and being able to recognize the most efficient strategies based on task context, individual's context, this sort of thing. Our own research has looked at an idea called adaptive number knowledge, and this is extended from this idea of procedural flexibility. And here we're looking at both with whole numbers and rational numbers, the idea that there's some students have this well-connected knowledge of numerical characteristics and arithmetic relations. And that this is actually, we found that it's distinct from just sort of typical procedural and conceptual knowledge, and that this actually predicts more beyond this procedural and conceptual knowledge. It predicts later algebra knowledge, as in it being important for future learning. So the task we used to measure adaptive number knowledge with rational numbers is what we call the arithmetic sentence production task, which is a bit of a mouthful, but yeah. And the idea is that students have 90 seconds to 2 minutes, and they have to come up with as many arithmetic solutions that equal a target number from a set of given numbers. So in this case, they have 1/4, 0.5, and then they come up with them. So you can see that this is a novel situation for them to have to apply their knowledge in new contexts. What we found is that even among the top 45 children, 45% of children in a group of 7th and 8th graders, there was a distinction. So even though they had similar levels of conceptual and procedural knowledge, over here, you see these top two groups in this latent profile analysis, they differed still in their adaptive rational number knowledge. So we can see that it's distinguishing, especially among these top performers. Right, so we wanted to design an intervention to promote this adaptive number knowledge. So we used this work by Feltovich and colleagues. Sorry, the citation's missing. But yeah, Feltovich and colleagues kind of outlined some features of learning environments that are going to promote this adaptive expertise. And of course, one of the main ones there being that they're involving meeting varied and changing demands instead of just these fixed class of problems that need to be solved skillfully. So one way we thought that these kind of learning environments could be designed is through digital learning environments, and especially digital games. So the first one that has been designed is called the number navigation game, and this was to promote whole number arithmetic. Students have to navigate around 100 square using arithmetic operations. So they're going from a target number to a given number to a target number. And there's different varieties of this task that force them to kind of use more complex arithmetic relations. We found that it had a slight effect on their arithmetic knowledge. In particular, with the older children in this intervention, it promoted their adaptive number knowledge and pre-algebra skills. With younger children, it more focused on this more procedural fluency and promoted that. So we found that this was a sort of promising means for promoting this adaptive number knowledge. So then we've then tried to apply that in working with fractions, rational numbers, excuse me. So this is the current study. It's a 7th grade intervention in the classroom. It was teacher-led. We had 8 intervention classrooms, 6 business as usual classrooms. Yeah, they were randomized at the classroom level. We combined 2 different games because we felt that it wasn't just necessarily that one game was going to capture all of the aspects of these rational number knowledge. As we saw today, there's many different kind of components, and we wanted to design it in a way that would lead towards this adaptive number knowledge. So we gave a teacher training and a pre-test, and then the teachers used, for 3 lessons, the number trace game, which we designed in a way that was just, that went much further than just estimating numbers on a fraction, on a number line that was bound from 0 to 1. They had to do things like cross notation estimation. We used unbounded number lines here. We used non-symbolic estimation. So for instance, here there's 0.3 is shown on the number line, and they have to estimate 2/5. And this involved a series of novel tasks as well. So they were always having to kind of work at the edge of their competence. And after this, they played the NaNoRobo math game, which was designed kind of based on the principles from the number navigation game. It was originally called the rational number navigation game, to give you a hint there. So again, they're moving from a particular point on the number line to a target. The number line can expand and contract depending on the distance between the two points that they're on. And again, we had different conditions that encourage them to use multiplication, division, and other kinds of more complex relations they had to estimate in a quick amount of time and these sorts of things. So it's a lot of varied tasks here. I'm actually not sure how much time I have left because you can't see the clock. I guess I should hurry. Yeah, our results just, we found that there was some differing effects, but we found an effect for adaptive rational number knowledge. This is a linear mixed model where it appeared that we should include classroom effects in the multi-level analysis, but those classroom effects weren't significant, but we did find an effect of condition. And you can see here the estimated marginal means controlling for pretest scores. We saw the experimental group outperform the control group. Obviously, we had large effects of pretest. We also found effects for their magnitude knowledge, and this was both comparison and number line estimation combined. Their representation knowledge through a number of varied tasks, for instance, converting between fractions and decimals, their mental calculations. But we didn't find effects for sort of this more routine conceptual knowledge, so factual knowledge about, for instance, the density of the set of rational numbers. Importantly, we saw that these effects seem to be stemming from their gameplay. So we looked at their game performance, both the quality of their performance and the quantity, how much they played and how well they did within the game. And we see that that predicts also their learning outcomes. So after controlling for pre-test scores, we saw the game performance predicted their post-test scores as well. So we see that it does appear to be that this game is having some effect on their adaptive rational number knowledge and other aspects of their rational number knowledge. Right, so in conclusion, we saw positive effects of the game-based learning environments. We do see that it might be possible to promote adaptive rational number knowledge. We didn't see the largest effects, but of course this was a very highly ecologically valid classroom intervention. It was teacher-led. We didn't kind of, the teachers used it how they would use the game sort of in their classroom to some extent. We gave them support and offered suggestions on how to use it, but yeah, things vary, obviously. And of course, the intervention and the actual tests were fairly far transfer tasks, that they weren't necessarily being trained for that specific task. And we saw that the quality and the quantity of the gameplay seemed to matter. But we don't know necessarily what those specific aspects of the gameplay of the learning environments were that supported the development. So we want to look into that further in the future. Yeah, but we do think that looking for novel ways to promote this sort of adaptive expertise beyond just the routine expertise are important, and that game-based learning environments might be powerful tools for this. Yeah, thank you to our funders, Academy of Finland, and the projects that we've been involved in the Growing Mind project, for instance. And yeah, thank you.
Thank you for your great talk, Jake. It's already past 9, but if people can stay longer, we can definitely stay here. I know people are very excited about the topic and we have many questions and comments. So if you guys can stay a little longer, we'll be here. Yeah, feel free to ask questions and make comments.
As people are leaving, I just want to say thanks so much to all the speakers and to all of you for taking time out of your day to come and listen to this. This is really exciting work, and we all know that fractions are hard, so I think these interventions are important, important advances to the field. So thanks, everyone.
Thanks. Have a great day. Bye.
I actually have a question for Alex, if I might.
Absolutely.
I recall on the second to last slide of your presentation, you showed, I think on the left side, some number lines, including one for fractions, one with the fraction of, oh, sorry, one for a whole number 6 and another for whole number 7. And I noticed that those two lines were the same length, which I expected they would be. But I wonder if that feature might be a problem for children. So for example, if you ask them to estimate 3/6 and 3/7 by analogy to whole numbers, they might imagine a line going from 0 to 6 and mark 3, and another from 0 to 7 and mark 3. But the lines themselves are the same length. So is that potentially a confusing feature? 7, in fact, is larger than 6, but they may miss that in the sort of visual uniformity of the presentation.
Yeah, absolutely. Great point. We have done a few studies where we ask kids to estimate whole numbers on number lines where the endpoint is changing. And kids definitely can do this. They are sensitive to like what that endpoint is. I see your point that the length of the line, the physical length of the line is not proportional to the size of the number. Yeah, I guess that is essential for making this alignment thing work.
Yeah, I guess it's a feature as far as fraction understanding is concerned, and it might be a bug as far as whole number understanding is concerned, right? If you were actually trying to represent 3, you would want it to be the same size no matter what the length of the number line. But in this case, you're sort of making the same number 3 be different sizes depending on the length of the number line. So I guess that would be accurate if you're trying to represent fractions, but inaccurate if you were trying to represent whole numbers. Is that right?
Right. Yep. Yeah, I think that's totally right. Yeah. And I think we're approaching this with the perspective that kids' whole number knowledge doesn't need as much help as their fraction estimation knowledge, right? Great question though. Thanks.
Okay, I don't know if we have other questions, but I wanted to thank you all for being here and remind about the questionnaire on the Qualtrics survey for scheduling next year. And also we're gonna be talking about working memory next week. I hope to see you all there. Thank you for the great talks and for being here a little longer. It was nice to see you all.
Thanks, Bella.
Yeah, thanks, Alex.
Thank you, everyone.
And Jing. And
yeah, great talks, you guys.
Thank you.
All right, take care.
Bye.
Good talks.
Thanks, John.